Welcome back to AGRON Infotech. In this clustering tutorial, we move from distance in a full hierarchical clustering. The goal is to see how customers group together based on spending behavior, how linkage methods change the dendrogram, and how to interpret the final clusters with both a PCA plot and a spending profile chart. I begin by loading Tidyverse and Dendextend. Tidyverse helps with data wrangling and plotting, and Dendextend helps me color dendrogram branches more clearly for teaching. Then I run a custom function to load the Wholesale customer's dataset. The function first checks whether the CSV file already exists in the working folder. If it does, it reads that file directly. If not, it downloads the official zip file from the UCI repository, saves it temporarily, extracts it, searches for the CSV, and reads it into R. I keep the argument that suppresses column type printing so the console stays cleaner while the video runs. Now I preview the dataset. The glimpse output tells me there are 440 rows and 8 columns. I can see 2 general information fields, channel and region, and 6 numeric spending variables: fresh, milk, grocery, frozen, detergents and paper, and delicatessen. Right after that, the summary output shows why pre-processing matters. Fresh spending ranges from 3 up to 112,151. Milk goes as high as 73498. Grocery goes to 92780, and the other variables also vary widely. This is an immediate warning that raw distance will be dominated by the largest scale variables. Next, I select only the 6 numeric spending features because this clustering lesson is about grouping customers by purchase behavior, not by category labels like channel or region. Then I scale the features. This step standardizes the variables so they contribute more fairly to the distance calculation. Without scaling, variables with larger raw magnitudes would silently overpower the rest. Now I compute the full distance matrix using the dist function. Here I explicitly set the method argument to Euclidean because Euclidean distance is the most common starting point for continuous numeric features, and it works naturally with hierarchical clustering in this example. This full distance matrix is not printed because it is very large, but it becomes the basis of the real clustering later in the workflow. At this point, I make an important teaching decision. Because the full dataset has 440 customers, any dendrogram with all labels would become unreadable on the x-axis. So for every dendrogram I show in the video, I create a small lineup. I set the random seed to 42 so the sampled customers stay reproducible. Then I choose a lineup size of 12, which is small enough to keep the labels readable, but still large enough to show real hierarchical structure. The sampled row indices are 49, 321, 153, 74, 228, 146, 122, 440, 128, 303, 24, and 327. I take those rows from the scale data and assign short row names so the dendrogram labels stay compact and easy to read. Then I compute a distance matrix just for this small lineup. When that output appears, it shows pairwise distances among the 12 selected customers. Some pairs are very close, like C228 and C122, with a distance of about 0.21, which suggests they are very similar in the scale feature space. Other pairs are much farther apart, like C24 and C440 above 8, which tells us those customers are very dissimilar. Now I compare the 3 linkage methods. I build one hierarchical clustering model with complete linkage, one with single linkage, and one with average linkage. In each call, I pass the same small lineup distance matrix and change only the method argument. Complete linkage uses the farthest distance between clusters, single linkage uses the nearest distance, and average linkage uses the average distance between all points across clusters. I arrange the plotting area into 1 row and 3 columns so the dendrograms appear side by side. I also widen the bottom margin slightly so the x-axis labels remain readable. In each plot, I set the main title, remove unnecessary x-axis and subtitle text, label the y-axis as height, slightly reduce the text size with the sex argument, and use hang equal to -1 so all leaves align neatly at the bottom. When the 3 dendrograms appear, the differences are very clear. In the complete linkage plot, the branching looks tighter and more compact because clusters only merge when even their farthest members are still relatively close. In the single linkage plot, the tree shows more chaining because clusters can grow through nearest neighbor connections. In the average linkage plot, the structure sits between the other two, producing a more balanced compromise. This comparison is one of the most important visuals in the chapter because it shows that the same data and the same distances can still produce different clustering stories, depending on the linkage rule. Next, I focus on complete linkage as the final teaching example. I set k equal to 3 because I want to cut the tree into 3 clusters. Then I plot the complete linkage dendrogram again for the same small lineup. This time I add rectangles around the clusters using the rect.clust function. The output is especially informative. One cluster contains C24 alone, another contains C146 alone, and the remaining 10 observations form the large third cluster. This tells me that in this lineup, C24 and C146 are strong outliers relative to the rest. After that, I create a colored dendrogram from the same complete linkage result. I first convert the clustering object into a dendrogram object. Then I color the branches using k equal to 3. When this plot appears, the 3 groups become easier to read visually. One branch is separated in red, one in green, and the large remaining branch is shown in blue. Because the lineup is small, all customer labels remain visible, and the audience can follow the tree naturally from leaves to major branches. Now that the dendrogram logic is clear, I switch back to the full dataset for the real clustering. I fit complete linkage on the full Euclidean distance matrix and then cut the full tree into 3 clusters using the same k value. After attaching those cluster labels back to the original data, I count how many customers fall into each group. The cluster size output is very revealing. Cluster 1 contains 429 customers, Cluster 2 contains 10 customers, and Cluster 3 contains only 1 customer. This is not a balanced 3-cluster segmentation. Instead, it tells me that most customers behave fairly similarly, while a very small set of unusual customers sits far away from the majority. In practical terms, this means the clustering is picking up outlier-like purchasing profiles more than equally sized market segments. Next, I use principal component analysis to visualize the full data clustering in 2 dimensions. I run PCA on the scaled spending matrix and keep the first 2 principal components. Then I create a tibble from those 2 columns and attach the cluster membership. In the ggplot call, I map the first principal component to the x-axis, the second principal component to the y-axis, and the cluster labels to color. I also set the point size and transparency so the cloud of customers remains readable. When the PCA plot appears, the pattern matches the cluster size table very well. The large pink cluster covers almost the entire dense cloud of customers. The green cluster appears as a small set of points separated to the left side of the plot. The blue cluster is only a single point far below the others, confirming that Cluster 3 is essentially one extreme outlier. This chart is very useful because it turns the numerical cluster counts into a visual cluster story. Now I move from visualization to interpretation. I summarize the original spending variables by cluster so I can understand what these groups mean in real units rather than scaled units. I group by cluster. Then I compute the mean of each spending category and drop the grouping structure at the end for a clean table. The profile table shows very strong differences. Cluster 1, the large majority cluster, has moderate average spending across all categories, with around 11850 for fresh, about 5,033 for milk, and about 6,977 for grocery. Cluster 2 has extremely high milk, grocery, and detergents and paper spending, with values around 34708, 48537, and 24875. That suggests a very distinct purchase pattern, likely much more concentrated in those product types. Cluster 3 contains only 1 customer, and its profile is extremely unusual, with very high fresh, frozen, and delicatessen spending, and very low detergents and paper. This explains why that customer separates so strongly from the rest. Finally, I reshape the cluster profile table into a long format and build a grouped bar chart. In the plot, I place the spending category on the x-axis, means spending on the y-axis, and use fill color for cluster membership. I dodge the bars so the 3 clusters appear side by side within each category. I also rotate the x-axis text slightly so the category names are easier to read. When the bar chart appears, the cluster interpretation becomes much easier. The bars for cluster 2 stand out sharply in grocery, milk, and detergents and paper. The bar for cluster 3 stands out in delicatessen, fresh, and frozen. Cluster 1 stays lower and more balanced across categories, which matches the idea that it represents the typical customer profile. This bar chart is the final bridge from clustering output to business interpretation. At this point, the whole workflow comes together clearly. I use the small lineup whenever I need readable dendrograms for explanation. I use the full dataset for the real clustering assignment. Then I interpret the result through cluster sizes, the PCA plot, and the spending profile chart. That gives both a clean teaching experience and a technically correct hierarchical clustering analysis. In the next video, we move into k-means clustering. There we compare tree-based clustering with sitter-based clustering and learn how to choose the number of clusters using the elbow method and silhouette scores.